Hello and welcome to section 5.2. This is the natural log function integration, and so here are the rules that we need to know. So if we're going to integrate 1 over x, we get the natural log of x, and they use absolute values for the function, and we'll talk about how those appear. And the same thing, if it was some other function, we'd say 1 over that function. Du turns into the natural log of the function. So this is just the reverse of the differentiation that we've been practicing the past few days. So we're going to move on. Make sure you get this down, and we'll talk about it as we go. So here's our first example, and so they're asking us to integrate 2 over x dx. Well, remember that this is a constant multiple of the 2, so I could write this as 2 times 1 over x dx. And so if that's the case, then when I integrate this, I get 2 times the natural log of the absolute value of x plus c. But then remember that this is really the power on x, so I can lose the absolute values because it's squared and it'll always be positive. And so we end up with something that looks like that for our answer. And so then our next example, they're asking us to use change of variables in this, and so they're asking me to integrate this. And so if I am, then I have to think about what my u value is, and my u value is 4x minus 1 if I differentiate that. So we're just going to do a u substitution. I get 4 dx. You'll notice there's no 4 over here, so it's still 1/4 du will equal dx. So I'm going to change this to 1/4 times the integral of 1 over u du. And this is basically the same thing we've been doing before. We're just trying to change it into an easier form for us so that we can get to our final answer. And so when I integrate 1 over u, I get 1/4 the natural log of the absolute value of u plus c, but I know u is 4x minus 1. So the natural log, 1/4 the natural log of the absolute value of 4x minus 1 plus c, and I'm still using my absolute values there, and that would be okay for my final answer for that problem. Another example, they could ask us to find the area of the region bounded by the x-axis and the line x equals 3. So basically they're asking us to find this area right in here. And so I just kind of sketched a graph for you so you could see it. The function I'm dealing with is y equals x over x squared plus 1. And so I have to integrate this to find area. That's what the terminology is for. So if I integrate this, I'm going to write this as x over x squared plus 1 dx. And I have to think of my u substitution. So u is going to be x squared plus 1. Du will turn into 2x dx. Well, again, I have 2 too many to get rid of that x dx, so it's going to be 1/2 du equals x dx that I can replace on top. That would be this guy right here. And so now if I go ahead and integrate, if I go ahead and substitute, I'm going to get 1/2 the integral of 1 over u du. And so it makes it much easier. So again, I get 1/2 the natural log of u plus c, and then my final answer, I can write it as 1/2 the natural log, and hold on, I'll come back to that. Should be this x squared plus 1, but you know what I forgot is that in this integral I want to go from 0 to 3 because that's what my graph is telling me. So all of these guys, well, I'm not going to go from 0 to 3. If I put 0 in, I get 1, and if I put in 3, I get 10. So really, I didn't have to do this plus c part. I could have left it like that and said, oh, well, if I'm going to go from 10, I'm going to do 1/2 the natural log of 10 minus 1/2 the natural log of 1. Well, the natural log of 1 is our magic number that we get, which is 0. So it's really going to be 1/2 the natural log of 10, and this is 0 over here. So we get approximately 1.151 when we're asked to find the area of this. So in my final example here, I've got a bunch, and we're just going to work through what the quotient rule and all of that stuff does for us. And so you may notice here in this first one, if I make my u x cubed plus x, then du will turn into 3x squared plus 1 dx, which is a very nice substitution for this because this now turns into the integral of 1 over u du, which when I integrate it, I end up with basically the natural log of u, which was x cubed plus x plus c. No big deal on that one. Now down here, we have to think about which function do I differentiate to get the other one? Well, u is going to be tangent of x, and when I differentiate u, I'm going to get secant squared x dx. So now I can replace that top line with du, and so I'm really dealing with 1 over u du again. So this makes this function much better, which gives me the natural log of the absolute value of the tangent of x plus c as my final answer for that one. The next one, well, maybe not quite as easy, but again, we're going to say u in this case is going to be x squared plus 2x. If I differentiate that u, I'm going to get, and remember this is u prime over u when we're dealing with these, so I'm not just making up where I'm choosing these from. I am usually choosing the bottom because that's where the u prime comes up, or the u is, and the u prime is on top. You'll notice I have 2 too many, so if I divide by 2, I can get the same thing that I have on top. And so all of this is the same as what we were doing before. Again, now we're just dealing with 1/2 the integral of 1 over u du, which then will give me 1/2 the natural log of x squared plus 2x plus c. And so that's the final answer for that one. And finally, when we get down to something like this, you'll notice that I have, in this case, again, I'm going to choose the bottom to be 3x plus 2. When I differentiate it, I get 3 dx, so I have 1/3 the amount I really need to replace my dx. So I am just looking at 1/3 of 1 over u du. And so again, just like in all our u substitution, we're trying to make our lives much easier. And so we are trying to simplify this as much as I can so that it's a nice, neat integral that I get to deal with. So this concludes our section in 5.2. If you have any questions, please come to class.